Hey, AP Chemistry, welcome to Chapter 12, Kinetics. We're going to talk through the beginning of Chapter 12, and this one is one of my favorite chapters. It's pretty black and white, it's very applicable, and it's pretty separated into a couple different sections. So the first section that we're going to go through is just defining rate. What is rate and how does it apply to chemical reactions? And then our next section is going to be over the physical manifestation or the mathematical manifestation of that rate, called the rate law. We'll go through a couple different applications of the rate law. We'll look at our third section, which is the kind of a second format of the rate law, and then we'll get into our last section, which talks about mechanisms and energies and tying the kinetic molecular theory into kinetics. So let's talk about rate, shall we? All right, so when we talk about a rate, rate is very ingrained in our lives in a lot of different ways. Anytime you drive a car, you need to be aware of your rate, right? So rate is going to be the, for a car, it's going to be the change in distance over the change in time, right? What rate is your car moving at? Well, that's your miles per hour. How many miles are you driving per hour? Distance over time. In physics, a lot of time when you're talking about rate, you're talking about speed, distance over time. You could be talking about velocity, which is distance over time with a specific direction in mind. Speed or velocity would be communicated in meters per second. That would be your units. But rate can be a lot of different things. Basically, rate is going to be anytime something changes over the change in time where that occurs. So acceleration is a rate as well. Acceleration is actually the change in speed over time. Well, we deal with rate in chemistry as well. And again, it's going to be a change in something over time. And so there's a couple different ways we can look at a chemical rate and discuss a chemical rate. Rate is all over our daily life. You see here that this sweet little face is very concerned with the rate of donuts being made, right? So rate in terms of a Krispy Kreme factory would be the change in donut production over time, or possibly the change in donut consumption over time. Could also be a rate inside the Krispy Kreme facility. So what does rate mean in chemistry? What are a couple different ways we can define rate and talk about rate in terms of a chemical reaction? Well, much like donuts, we can talk about a rate of production. So that would be looking at the products in a chemical reaction. Reactants go to products. So when we're looking at a chemical reaction and we want to talk about the rate at which that chemical reaction is proceeding forward, we could look at how many products are being made. So the change in product, probably in terms of some type of concentration, right? Most likely molarity if we're in our chemistry class, over the change in time. That would be one way that we could look at the rate. So if 5 moles of our product are being made every second, our rate would be a positive 5 moles per second, moles per liter per second, right? We could also look at rate in terms of the reactants, much like a donut factory. the Krispy Kreme donut factory is concerned about how fast they're selling donuts or how fast donuts are being consumed, we can look at rate in this way for a chemical reaction as well. So that would pertain to the reactants, right? So rate could be defined as the change in reactants over a change in time. Again, we're probably going to look at this in terms of concentration. So what if 5 reactants are being used every second? Well, then our rate would be, if the change is going to be defined as final minus initial, right? If we have less in the end than we do in the beginning, then our rate would be negative, right? So let's say we start with 10 moles of our reactant and we end with 5. So final minus initial would be a negative number in that amount of time. We would get a negative 5 moles per second for our rate. So we can communicate this rate in a couple different ways. The appearance of product, the disappearance of reactant, and as our reaction gets more complicated, so do our options for communicating rate. Let's look at this a couple different ways. Okay, so increase in concentration of product, which would probably be a positive. The decrease in concentration of a reactant, which would probably be communicated as a negative since it's a decrease. In chemistry, we deal with the amount that's present. Usually we're talking about a molarity, right? So usually we're going to have molarity per second, would be this one. Or if you want to break that apart, you could go moles per liter per second. Okay, so as our reaction gets a little more complicated, so do our options for communicating rate, right? So in this reaction up here, I have 1 reactant, but I have 2 products, right? If I want to know the rate of my reaction, I can communicate it in terms of the disappearance. That would be this one. Disappearance of my reactant. I could communicate it in the appearance of my ClO3 minus ion. What is that? The chlorate ion. I could also communicate it in terms of the rate of appearance of the chloride ion. So as my reaction gets more complicated, I have more options as to how I want to communicate this rate. However, these are not all going to be equal values, right? So let's say that 3 okay, let's be consistent here, shall we? Remember this table? We've dealt with this table before. We like to call it the ICE table. Sometimes this E is not an E, sometimes it's F. So it's either initial change equilibrium or initial change final. Since we haven't really talked through equilibrium really in detail yet, it might look more like an IC table rather than an ICE table, but that's okay. So this bottom one, for now, we can do either equilibrium or final. So let's say, I don't know, we have 100 of each molecule, right? The initial doesn't really matter. So I'm just putting a value in for initial that we can kind of ignore. Okay, so let's say 3 of my hypochlorite ions disappear, right? My reactant, my ClO minus. So -3 is my change. So my rate in terms of this is going to be 100 minus 97, right? So my change is going to be 3 per second. Okay, so my chemical rate is 3 molar per second, right? Well, is that consistent if I look at the other two things in my reaction? Let's find out. If I use 3 of my hypochlorite ion, how many chloride ions am I going to make? I'm going to make 2, right? That's what these coefficients mean. If I use 3 of this one, I am going to make 2 of this one and 1 of this one. Okay, so this tends to kind of blow our minds once in a while. So we can actually draw this out. So let's make chloride blue and oxygen, let's make it purple. Okay, so here's my reactants. And then as the reaction proceeds forward, I'm going to get 2, chlorides were blue. Okay, I'm going to get 2 chlorides all by themselves. And then I'm going to get a 3rd chloride that's attached to my 3 oxygens, right? So remember, when you're looking across a reaction, remember, there's a conservation of mass. The mass that you start with in the beginning is the same as the mass that you end with. There's a conservation of atoms. The atoms that you start with are going to be equal to the atoms that you end with. We start with 3 chlorine atoms and 3 oxygen atoms. Notice we end with 3 chlorine atoms and 3 oxygen atoms. Our atoms are conserved. Our molecules are not conserved, though. We start with 3 molecules. We end with, I guess we end with 3. Okay. Sometimes they're conserved. Sometimes they're not conserved. They're not necessarily conserved, right? So we could start with 3 molecules in this case, and if they're all broken apart, we would end up with 6 molecules. So molecules are not always conserved, but atoms will be, mass will be. So the molecules you have to be really careful of. The molecules, you need to look at the coefficients to figure out how many molecules are being consumed, how many molecules are being made, because number of molecules might actually change. And that's what kind of throws our rate off. So if we look at rate in terms of the production of the chloride ion, right, I'm going to have 2 chloride ions being made. So that's going to be the positive, 2 molar. Oh, you want a big M for that. 2 molar over 1 second. So my chemical rate of this reaction is 2 moles per second, right? Or is it 3? Is it 3 moles per second? Or if we look at the chlorate ion, let's do this one, shall we? Okay, in 1 second, I'm going to produce 1 mole per second. So what's my rate? Is my rate 3 moles per second? Is my rate 2 moles per second? Is my rate 1 mole per second? Well, it depends. It depends on your perspective. What are you communicating this rate in terms of? So if you're going to write rate like I just wrote rate, you better specify what you're talking about. 3 moles of ClO minus per second, 2 moles of Cl minus per second, 1 mole of ClO3 minus per second. Which of these rates is correct? They all are. They're all rates, but in terms of different molecules within the equation. So that's the first thing to know about a chemical rate, right? It depends on your perspective. And you better be clear about what your perspective is. Otherwise, the rate that you communicate isn't going to mean a whole lot. Now, there is a way around this, and that's kind of what, after we're done talking about rate in general, that's kind of the next thing we're going to go to. We're going to go look at something called a rate law, because a rate law has certain specifications that surround it. And so it's always consistent. And any scientist can look at that rate law and understand what it means without additional context being given. But for now, no, we can communicate a chemical rate a couple different ways. So you need to be really clear about what your context is so that your rate has meaning. Lots of graphics on this one. So nice. Okay. There is a way we can take this rate and make it equal. Full disclosure here, not my graphics. They're cute and all that, but I didn't make them. Okay, anyway, because we can define rate according to any molecule inside our reaction, like I said, we want to move towards this more consistent view of looking at a chemical rate. So when we define rate in terms of one molecule in our reaction, there is a way we can make these rates equal. We can make these rates equal to a consistent rate. So if you take that rate we just built, so this one was going to be 1 molar per second. This next one was going to be 2 molar per second. And this last one was going to be 3 molar per second. Notice we can, -3 molar per second. Notice we can make these rates consistent by dividing by the coefficient. So the coefficient of this first one that I wrote is a 1. The coefficient of the second one I wrote is a 2. And this one's a 3. So notice if I do that, all of a sudden I come out with a rate that is, for each one of these, consistent. Now notice it's still going to be positive for the products. It's still going to be negative for the reactants. Remember, products are appearing, reactants are disappearing. So you want that communicated through the sign of your rate. But it gives us an equal or equivalent rate depending on the molecule we're talking about. So this is one way you can take your rate and make it more consistent. You define the rate in terms of concentration per time, and then you divide by the coefficient. So concentration change per change in time times the coefficient. And then remember, you need a sign that tells you, is it going to appear or disappear? And that can equal an overall rate for your equation that's a little bit more consistent and not quite as variable depending on the molecule that we're looking at. Again, with the arrows. Okay, so here's a general form of our equation. I don't know why the D got put. We'll put the D back where it's supposed to be. And notice we now have a general rate form for products and reactants, and really they should only differ in sign. Okay, so this is a good one we can come back to with these concepts, and we'll practice it together. Here we have this idea that we've been talking about communicated graphically. So let's look at this a little bit. We're going to look at concentration, changing concentration over time. So take a look at this and think, okay, I have a red line here. What is that red line communicating? What is A? Is A going to be a reactant, or is A going to be a product? So it'd be a good time to pause and make sure you have kind of a justified guess before we talk about it together. I want you to think through this on your own and then compare to what we come up with together. Okay, so notice A is diminishing, right? We start at number of moles for A at 1, and as the reaction proceeds forward, notice our x-axis is time. As our reaction proceeds forwards, we get less and less and less moles. So A is going to be our reactant. Let's take a look at B. What's this blue line representing B going to be? We start at 0 moles and we get more and more and more. So B is going to be a product. Okay, so here's our general form of the reaction. Now I want you to look at the numbers and see, is this a 1-to-1 relationship? Is it a 1-to-2? Is it a 2-to-1? What's our relationship here between A and B? Again, pause for a moment and figure out, look at the graph and see if you can figure that out. Okay, and we can do that by comparing points here. So our 2 points at 10 minutes, A has decreased by 0.26, B has increased by 0.26. Again, at 20 seconds, we see another decrease of, what is that, 0.2, increase of 0.2. So they are changing at the same rate. If I look at this line right here between these first 2 points, I can figure out the change in the rate by looking at this graph. I have change in number of moles, so that's 0.74 minus 1, which is going to be 0.26. This is for A, and that happened inside 10 minutes. Okay, so my rate of A between those first 2 points is 0.026 moles per second. Let's look at B, shall we? Okay, so B, I'll do down here at the bottom. Again, we can look at this change between these first 2 points. Okay, so B is going to start at 0. It's going to finish at 0.26. I'm going to go final minus initial over my change in time, which is 10 minutes. So I get a 0.26 molar over 10 minutes. I get a 0.026 moles per second to the -1. Oh, and this one, sorry, I should go final minus initial, so that one should come out to be -0.26, -0.26. Okay, so notice my rates are equal, opposite in sign, equal in magnitude, which tells me that they are decreasing and increasing at the same rate. So this is going to be a 1-to-1 relationship. Okay, pause here real fast and let's reflect a little bit. So first of all, I calculated a rate based on a graph, right? By ultimately calculating what? What did I just calculate? Change in moles over change in time, change in my y over change in my x. What is that? What's a change in y over change in x? It is slope, right? So the slope between 2 points can give you the rate between 2 points. Now, if we look at these 2 points, notice it's not necessarily a straight line between those 2 points. So what I just calculated was an average rate. If you use the slope to calculate rate, like we just did, that's going to give you an average rate between those 2 points, not actually an actual rate. So dig deep into your math background. What would we call the other type of rate? If I want the rate that happens at this exact point in time, what would I call that? I'd call it an instantaneous rate, right? So we have two different types of rates going on here. We have an average rate between 2 points. I can use slope to calculate that. At a specific point in time, however, I would have to calculate an instantaneous rate. And how would I do that? Dig deep into your math. Oh, aren't we so thankful for math classes at this point in time? You would need a tangent to the line to calculate your instantaneous rate, right? If we want the rate at 1 point, we need a tangent line. If we want to calculate the rate between these 2 points, really we're getting into integrals here and again into calculus. Now, calculus, you may or may not be thankful for this, is beyond the scope of our class. We're not actually going to go into calculus, but it is healthy for us to recognize the limitations of what we're doing, right? If we're going to use the 2 points to calculate slope, we're going to calculate an average rate between those 2 points, not an instantaneous rate, right? Also notice another thing here. Look at the slope between these 2 points. Okay, notice, is it the same? If I were to calculate an average rate between these 2 points, is it the same as the average rate between my original 2 points? 0.26 to 0.46. So the difference there is 0.2 over another 10 minutes. No, that's not going to be the same. It's going to be a different rate. So as my reaction proceeds, my rate changes. And why does this happen, right? We can think back to the kinetic molecular theory in order to explain this happening. What do you need in order for a reaction to happen? You basically need 3 things. Can you name what those 3 things are? You need a collision. You need that collision to happen with enough energy, and you need that collision to happen with the right orientation, right? So in order for a reaction to happen, we need those 3 things to occur. Well, in the beginning of our experiment, we had lots of things present, right? We had lots of A present. So we have 1 mole of A present hitting each other, hitting the walls of the container, flying around, right? Well, if that's what makes the reaction go forward, if collisions of A with A make the reaction go forward, well, at this next point, we have less molecules. We only have 0.74. And then we have less molecules and less and less and less. And by the time we get down here, we only have 0.16 moles of A left. And they're not going to hit each other as often. There's less of them there. Think about little kids in a room. If you put little kids in a room and you give them lots of sugar, you're going to have lots of collisions, right? This is just what little kids do. They run and jump and they're free spirits and they have no idea what's around them. And so they hit other people a lot. Well, if periodically you take little kids out and by the end, if you started with 20 kids in a room and by the end you only have 2, you're going to have less collisions. If you're a parent, this is a good thing. If you are a chemist who wants your reaction to proceed forward, this is not necessarily such a good thing, right? So less molecules present means less collisions, means less reactions, means a lower rate. So notice one of the other things we can draw off of this graph is that our rate is not consistent. In the beginning, our rate's going to be higher. In the end, our rate's going to be lower. And this is true anytime your rate is dependent on molecules hitting molecules. Now, not all rates are dependent on molecules hitting molecules. We will look at a case where the rate is independent of molecules hitting molecules. But for now, the rates that we're talking about, you need to have a collision with enough energy and the right orientation. And so the more you use of your reactants, the slower your rate is going to go. Okay, lots of conclusions off of this graph. It might be a helpful time to pause and just kind of list some of those things for yourself. See if you can do it from memory. Just repeat it one more time before we go on. and talk about the next part of rate. Oh, and again with the lines. Okay. This just says basically the same thing we just said, only they give it to you in a data table instead of a graph. Notice, again, you can see by looking at this data that rate's not constant. It is going to decrease over time. We have a really similar reaction here going on. We have one molecule as the reactant, NO2, nitrogen dioxide. And in order for this reaction to proceed forward, nitrogen dioxide needs to collide with nitrogen dioxide. And so the less nitrogen dioxide you have as this reaction proceeds forward, the slower your rate's going to go. And you can see this in the data. Notice that our data here is being communicated in terms of the disappearance of nitrogen dioxide over time. And at first we start at 4.2. Notice that all of the exponents are consistent, so we can kind of ignore the exponents and just look at these base numbers. Okay, so 4.2 in the beginning, 2.8, 2.0, 1.4, and by the last 50 seconds that are tracked, your rate is actually 1. So rate has significantly decreased as this reaction proceeds forward. Exactly what we saw on the last graph that we looked at. Okay, so if we are going to calculate an instantaneous rate off of a graph, we would have to use a line that is tangent to the slope at that specific point in the graph. Now this is cumbersome to do, to use a tangent. It's also pretty cumbersome to use an integral with calculus. And so when we design an experiment, we want to design an experiment in the easiest way possible. That's going to give us the most consistent data. We're probably not going to design an experiment that we need an integral or a tangent in order to get our conclusion. Okay, so we have talked about the collision theory a little bit, right? We talked about how you need a collision with enough energy and the right orientation in order for a reaction to occur. The other part of the collision theory is that there are a couple of factors that can change the rate at which this reaction is proceeding. And we've already talked about one of those factors. It's concentration, right? The less of our reactant we have, the slower our rate is going to go. Can you think of other factors that might be part of this? This would be a good time to pause the video, jot some thoughts down, and see if you can come up with some of these. Okay, so there's this little video. You may have seen it before. I tend to love this little video. And it talks about those factors in the collision theory that are going to affect the rate of reaction. So we're going to spend a little time and watch this. This is a TED Ed video about how to speed up chemical reactions. So you're looking at factors that affect the rate of a chemical reaction. See if you can find the 5 factors inside this video.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have two important characteristics. One, correct orientation that allows books to be knocked from one's hands, and two, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date for the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has some more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing 2 particles together and orienting them correctly in space so that the 2 can meet at the correct configuration and allow a reaction to take place. So to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Okay, there you go. Now, don't say it. I never did anything to help you out. There you go. How to get a date for the dance and speed up a reaction. So there's our collision theory. Notice he said it in the beginning. Collision has to happen with enough energy and the right orientation, right? And so there's 5 different ways we can manipulate our reaction in order to change the reaction rate. Smaller volume, so same concentration in a smaller volume. Number of students in the hallways, so that was our concentration. Faster speed, so that is raising the temperature. What else did he do? Catalyst, using a matchmaker, and surface area, so breaking up clumps or increasing surface area. And this is why, like, grain silos. So it doesn't happen a whole lot around here, but in the Midwest where I grew up, grain silos exploded once in a while because when they're filled with grain, the grain is flammable, sure, but it'll burn just like wood does. When the grain silo is empty, it's filled with grain dust. And so the whole thing can burn at the same time, which causes an explosion. Same thing with like coal mines. Coal dust is much more explosive and dangerous than actual chunks of coal, which the outside will burn, but the outside has to burn before the inside can. Same thing with like a tank of gasoline in your car. If your gasoline tank is full in your car, then just the top surface can start burning, right? It's going to burn just like a log is going to burn. But if the tank is empty and filled with vapor, then the whole tank, every single particle in the tank can burn at the same time. It's all exposed to the reaction, and that'll cause an explosion. Okay, so that's the collision theory and the 5 factors that can speed up or slow down your reaction inside your collision theory. So from this point, now here's a nice little graphic thing about instantaneous rate. We're going to get into our math expression of rate, which is called the rate law. So this is kind of part 2 of chapter 12. This is a good place for us to stop for now. Let me know what questions you have. We'll do some practice with this. I'll see you in class.